An anonymous function can use variables from the function that surrounds it. When it does, we say it closes over them. It keeps them alive, and it keeps seeing their current values. That is a closure, and it is how you build a function with a memory. It is also where the single most famous Go bug lives, so we will spend real time on that at the end. Start with the smallest example that shows the idea. Increment takes no parameters and declares no variables of its own. It reaches out to count, which belongs to the function around it, and changes it. So the first call gives 1, and the second call gives 2, because the change the first call made is still there. This is the sentence to hold on to. The closure captures the variable, not a copy of its value. There is exactly one count in this program. Both the outer function and the closure are looking at the same one. Everything else in this video follows from one rule, so here it is on its own. A closure captures the variable itself, not a copy of its value at the moment you wrote it, the actual variable. If you understand that sentence, the useful behavior and the famous bug are both obvious. If you do not, both of them look like magic. Now it becomes a tool. Look at that signature. Counter takes nothing and returns func open bracket close bracket int. It returns a function. Inside, it makes a variable n and returns a closure that uses it. And here's the strange part. When counter finishes and returns, n should be gone. It was a local variable in a function that has ended. But it is not gone. The closure is still holding it, so it stays alive. Go noticed that n outlives the function it was declared in, and quietly moved it from the stack to the heap for you. No manual memory management. No dangling pointer. It simply works, and the garbage collector cleans it up when the closure itself is finished with. This is the part that shows what is really happening. We call counter twice, getting 2 closures, A and B. Counts 1, 2, 3, as you would expect. And B counts 1, not 4. Each call to counter created a completely fresh n, and each return closure is holding its own. They are the same code, with separate state. That is worth sitting with for a second, because it is the mechanism behind everything in the rest of this video. And this is the most common practical use, a function that builds a specialized function. Multiplier takes a factor and returns a function that multiplies by it. The returned closure captures factor. That is the whole trick. So double is multiplier of 2, and triple is multiplier of 3. Double of 10 is 20, triple of 10 is 30. Same code, different captured state. You have just written a tiny factory in 5 lines and with no classes involved. This same shape is how middleware, retry wrappers, and rate limiters are written in Go. Each one is a function that wraps another function and returns the wrapper. Remember the defer video, where a deferred call's arguments were frozen at the moment you wrote defer? Closures are the fix for that, and now you can see why. We are not deferring a call with arguments here. We are deferring a whole function that takes nothing. There are no arguments to freeze. So when it finally runs, it reads total right then, at the end. Total has become 15 by that point, and 15 is what prints. This is the standard way to log a summary on the way out of a function, or record how long something took, or inspect a result just before returning it. And now the bug that every Go programmer writes exactly once. We build a slice of closures inside a loop. Each closure prints name. Now apply the rule. A closure captures the variable, not the value. So which variable is each of these 3 holding? In Go 1.21 and earlier, there was only one name variable, reused by every pass of the loop. All 3 closures captured that same one variable, and by the time you called them, the loop had finished, and it held its last value. So all 3 printed C. This caused so many real bugs, particularly with Go routines, that the language itself was changed. Since Go 1.22, each iteration of the loop gets its own name, so the same code now prints A, B, C. That is a genuinely unusual thing for a language to do, because it changed the meaning of existing programs. It was judged worth it, because almost every program relying on the old behavior was relying on it by accident. Before that change, this was the fix, and you will still find it all over existing Go code. Name: equals name. That line looks absurd until you know what it is for. It declares a brand new name inside the loop body, which shadows the loop's one and copies the current value into it. Now each pass of the loop has its own variable, and each closure captures a different one. On modern Go, this line is redundant, and Go Vet will not thank you for adding it to new code, but in older code it is load-bearing, and deleting it would reintroduce the bug. So when you see it, you now know exactly what it is doing and why it is there. The language change fixed the common case, but the underlying rule has not changed at all. So whenever a closure outlives the loop that made it, stop and ask which variable it is actually holding. Goroutines are the big one. Because a goroutine started inside a loop almost always outlives that loop. Get in the habit of asking now, while the examples are small. 4 things to keep. A closure captures the variable, not a copy of its value. Everything follows from that one line. Captured variables outlive the function that declared them. Go moves them to the heap for you, automatically. Each call to the outer function creates fresh state, so 2 closures built the same way are completely independent. And defer a closure rather than a call when you want it to see the final value. Those 4 cover every closure you will write. Your turn. Write accumulator. It returns a function that adds its argument to a running total and gives back the new total. So calling it with 10, then 20, then 3 should print 10, 30, 33. Pause and write it. Here's the answer, and it is the counter from earlier with one change. The returned function now takes an argument. Total lives in accumulator, gets captured by the closure, and survives after accumulator has returned. 10, then 30, then 33. The running total is remembered between calls, and it lives nowhere you can reach except through that function. That last part is worth noticing. Total is genuinely private. No other code in your program can see it or change it, because there is no name for it anywhere else. And that completes the functions module. You can declare them, return several values at once, take any number of arguments, treat them as values, and give them a memory. Next module, the containers you will actually put your data in. Slices, arrays, and maps. And that will finally explain the thing we have hand-waved twice now, why a slice passed to a function can be modified by it.